Today we are diving into chemical kinetics, which is all about how fast reactions go. We'll explore what the rate of a reaction means, how we define it, what affects it, and how we write down rate laws and integrated equations. We'll also peek at collision theory, activation energy, and the Arrhenius equation. First up, let's compare average and instantaneous rates. Here's a concentration versus time graph for a reactant. Average rate is the change in concentration over a time interval, delta bracket A divided by delta T. Instantaneous rate is the slope of the curve at one point, which is the derivative d bracket A over dt, and it tells us how fast the concentration is changing right now. Next, let's look at the three main factors that tug on reaction rate. Concentration matters because more reactant particles bump into each other more often. Temperature matters because hotter particles move faster and collide with more energy. A catalyst gives the reaction a new lower energy path, so more collisions lead to products. Now we can talk about order and molecularity. Consider a reaction A plus BB forms products. The experimentally determined rate law looks like rate equals K times concentration of A to the power M times concentration of B to the power N. The overall order is the sum M plus N, and it tells us how the rate depends on concentrations. Molecularity refers to how many molecules collide in the elementary step, which is either unimolecular or bimolecular. Let's dig into integrated rate equations for zero and first order. For a zero-order reaction, the concentration decreases linearly. Bracket A at time t equals bracket A naught minus kT. The half-life for zero order depends on the starting concentration. T half equals bracket A naught over 2K. For a first-order reaction, the natural logarithm of bracket A at t equals natural log of bracket A naught minus kT. The half-life for first order is constant and equals natural log of 2 over k. Collision theory gives us an elementary picture of what must happen for a reaction to proceed. Particles must collide. They must collide with enough energy to climb the activation barrier, and they must be oriented correctly. The result is that only some fraction of collisions are fruitful. Finally, we'll wrap up with activation energy and the Arrhenius equation. The activation energy is the energy hill that reactants must climb. The Arrhenius equation relates the rate constant K to a frequency factor A and the activation energy. K equals a times e to the negative E sub over RT. A higher activation energy makes K smaller, and a higher temperature reduces that negative exponent, so K grows. That wraps up our tour. Reaction rate depends on particle collisions, concentration, temperature, and catalysts. Rate laws tell us how concentrations affect the speed, and integrated equations help us look back in time. Collision theory, activation energy, and Arrhenius give us intuition about why some collisions become products while others do not.